My name is John Hawkins, and I work in machine translation, but I'm very pleased to be introducing to you today somebody who works in computer graphics. He's worked at DreamWorks and did his PhD at Carnegie Mellon. He's currently working on his own projects under the umbrella of Spotworks. He's going to be showing us some of the Spotworks Productions art today, and also talking extensively about the electric sheep screensaver. Without any further ado, I'll give you Scott Draves, also Spot.
Thanks, John. Let's see if we got all of our technology straight.
Spot, can you move a little more to the center so I can catch you? Thanks, that's good.
So what are you seeing right here? This is Dreams in High Fidelity, and it was made with the electric sheep screensaver. And I'm curious, how many people here already have seen the electric sheep or know what it is? Okay, that's cool. It's about half of you. And so some of you, you can probably immediately see some differences between the screensaver and this. And what I'm going to talk to you about today is, what this is and how I made it. And I'm going to go into a lot more technical detail than I usually do. And I hope you appreciate that. And so what is this? It was made with evolution and mathematics. None of this was drawn or modeled or designed by me. And it's really the creation of a cyborg mind composed of 30,000 computers and people all over the world, mediated by a genetic algorithm. And it would have taken over 100 years for one computer to render this whole thing. It's over 1 hour of work per frame. So, but I'm not going to leave it up for the whole talk, because I know you won't remember anything I say. So we're going to have to turn it off. And I was told to push this button. Oops. Okay. And can you mute that or turn it off? Oh yeah, and it never repeats, plays indefinitely, and it's self-contained. So it's running off of the little shuttle PC that's sitting over there. So I wasn't kidding when I said mathematics. Here's some equations. Every image that you saw is the solution to an equation. And if you think of the plane R2 and there's some set S, which is the image, a part of the plane, which is what you're looking at, S, in this case, is defined to be a solution to this recursive set equation, and where these functions f sub I are map the plane to the plane, and this is sort of these things called iterated function systems are standard textbook kind of fractal, been around since the 80s, and this is sort of the kind of images that they produce. The one on the right is called Sierpinski's gasket, and the one on the left is Made Barnsley's career. It looks like a fern. And people were amazed that a natural-looking image, like a fern leaf, could be defined or produced or modeled with a couple of matrices. But that's the magic of fractals. So that's sort of where we started. And in 1992, I was I was working to create better visualizations of this kind of process. And so I made 3 improvements to iterated function systems. One was replacing those matrices with nonlinear functions. The other is adding color, in particular adding color by structure. And the third thing was tone mapping, which is a way of handling large dynamic range in an image. And so what it comes down to is this rendering algorithm, the thing that the algorithm which draws all the pictures that you just saw, is really, it's like a particle system, which is a standard thing in computer graphics where instead of drawing polygons or circles or lines, the image is drawn with thousands or millions, or in this case, actually billions of little dots, just like, imagine them as being particles of dust, which are all moving intelligently and can reform into any shape. And the way the rendering algorithm works is it's a stochastic algorithm. It's quite simple. You've got a bunch of these functions from the plane to the plane, these transformations or mappings. And the way it works is you draw a dot on the screen, you draw a particle, a random one, anywhere on the screen, and then you pick one of the functions at random. You have like a collection of functions, maybe 2 functions, maybe 5 functions. You pick a function at random, you apply it to that point, it gives you a new point, and you draw that point. And then you just repeat. And so you draw points, you draw dots all over the screen, and if you draw enough dots, eventually the image emerges out of them. So here are the functions, or here's what some example of the functions that we use are. They're just kind of little blobs of algebra. They don't have any special mathematical properties. They were picked because they look good. And they are composed with the linear functions. So this AIX part is a linear function, and then you compose, there's a blending vector, the little v sub I, v sub j things, which is a knob for each of the nonlinear functions, which says how much of it is present. So the color comes from adding a third coordinate to the iteration. So instead of just having points on the plane with 2 coordinates that get bounced around, you actually have points in a 3-dimensional space. And the third coordinate is looked up in a palette before it gets drawn. And this is a different way of, there's lots of ways of adding color to iterated function system image. And the way that people did it previously was usually coloring by density, which is kind of the scientific approach to visualization, where, you know, like, you can imagine like an infrared picture where like the parts that are less dense or have less particles get like colored in blue, and the parts of the image that are more dense or have more particles, you know, get colored in like red. The problem with using that kind of coloring or that kind of palette is that it's, as the image moves, the different parts of it change color, and that doesn't look natural. It doesn't look like an object in motion. It looks like you're wearing infrared goggles or something. So doing it like this is important to make it look realistic. Another thing that's important is that it actually is using a palette, which is sort of like, a list of 256 colors, derived from data. It's not algebraic. A lot of people who use or do genetic algorithms to do graphics, you have some formula which gives you RGB values, which is the colors that get drawn on the screen. And when you do that, you end up with colors that look kind of very RGB, or they don't have any kind of coherence. And the colors here were originally derived from, the palettes were originally derived from, natural things like photographs of landscapes or like paintings by famous people. And there's an algorithm which can like derive the palette, and then that was the source of all the original colors. So makes it look much less mathematical. And so these are the kinds of images that that this fractal flame algorithm produces. And these are the actual files that I rendered back in 92 or 93, I think. So just to review the genetic code here, or the parameter space, or the thing that produces the images, there's 250 floating point numbers in the genetic code. that comes from all those matrix coefficients, those 2 by 3 matrices, and then all the coefficients for the nonlinear functions. And notice it's what I described as strictly a two-dimensional process. You have points in the plane, and they have color, but you're drawing them. And as you'll see, I'll show you some examples. The results sometimes look three-dimensional, and there's a sort of an interesting kind of trick that produces that I'll explain. But what I want to emphasize here is that the image is sort of emerges, or is a resonance that comes from these geometric transformations. So it's not images that are drawn, or it's not geometry that's drawn. So it's not using your 3D graphics card it's really just a simple C program that sort of solves this equation. So, but it's a simple program, but it can have some rather interesting results. Here's one that appeared a couple months ago. And I'm showing you this one in particular because it has this 3D illusion. If you look at the blue arcs in the middle in particular, to me it sure looks like those blue arcs are over the yellow or in front of the sort of orange background. So how did a 2D algorithm do that? There's a close-up. And so the answer is this tone map. So the way the images are drawn, the brightness of any one pixel is proportional to the logarithm of the number of particles that are in it. And the reason it does that is because there's a really wide dynamic range of densities. Like many natural phenomena, it follows a power law, and you'll have some pixels that might have 5 particles in it or 10 particles in it, and you'll have some other pixels in another part of the image that have 500, and another part of the image it might be 50,000 or 1,000,000. And so it's difficult. If you just displayed a linear mapping between the number of particles and sort of the brightness of the pixel, you'd end up with a few pixels that were completely white, but most of the image would be completely black. And so you need some kind of dynamic range compression in order to be able to sort of see the image, see all the information in the image. I mean, photography and computer has the same problem, and computer graphics has had this problem for a long time. How can you represent brightnesses that vary from the sun to a dark room with just 8 bits? And so you can't. You have to squeeze things down somehow. So I use the logarithm, and it has this interesting property that say you have 2 parts of the fractal, one with a density of 100 in orange and the other one with a density of 1,000, which I drew in blue. The place where they cross has a density of 1,100, but the logarithm of 1,100 is only slightly greater than the logarithm of 1,000. And so the area where they cross looks the same as the one that's in front. So more or less, the way the algorithm draws, whatever is sort of more dense appears to be in front, even though there's no z coordinate, there's nothing actually happening in 3 dimensions. So this didn't happen by design, but just one of many things that just kind of accumulated along the way. So what I described so far was an algorithm that can take a genetic code, which is a set of these transformations in the plane, and creates an image. But it's just a still image. So where did the animation come from? And the answer is, pretty simple. By changing the parameters in the genetic code, by changing some of those floating point numbers over time, then the resulting image solution changes over time, and that's animation. So specifically what it does is it uses the matrices that's in the genetic code, and it just applies rotations to those matrices. And the nice thing about rotations is when you're finished rotating, you're back to where you started. And so therefore the animation that gets produced by rotating one of these matrices is also the image ends where it started, so the animation loops, which is makes them useful for VJing, for one thing, but also makes them very hooked together in this really nice way for playback. So it also makes transitions, so between any two parameter sets, between any two genomes, you can do a smooth morph by interpolating in the genetic space, and then you'll also get an interpolation in the image space that has the same endpoints. And it uses sort of splines in order to get C1 continuous motion, when that means motion that doesn't have any sort of jerks or jars in it, because it's possible to have continuous motion that still has an angle in it, and that sort of feels unnatural. And the end result is that you can interpolate between any two, genomes, but it actually only has can render, a few of them. So what you end up with is a graph of video after you've rendered a bunch of sheep. And so here we have the blue circles represent individual parameter sets or particular genomes. And each edge in this little graph I've drawn is a segment of video that gets sort of rendered. And so as you're watching the screensaver, or as you're watching the high fidelity version of it, what the computer is doing is more or less wandering through this graph, where just following the edges sort of head to tail, and every time it plays a piece of video, and then wherever you are in the graph, there'll be multiple possible successor video clips that smoothly transition from wherever you are. And this is how it gets how it doesn't repeat, even though it has only a finite amount of video on the hard disk, because your computer may have, because you can sort of go through this graph in a non-repeating pattern, you can make a non-repeating movie out of a finite amount of content. So here's some examples of animation, just in film strip. So it's showing how from one particular image in the upper left, it's got showing 8 transitions to 8 other sheep, and you can see that each one is a smooth morph, and which is much more interesting than just crossfading. So the genetic code gets stored and communicated in an XML format, which is pretty arbitrary. And it has all the parameters for the coefficients written down here. And on average, these genetic codes are 1.7 kilobytes each. And I came up with that number not just by measuring the size of it, but by taking a whole bunch of them and gzipping them, and then measuring that. So that's more of more telling. It tells you how much sort of information is really in the genetic code rather than how many characters it takes to store. So it's really minuscule relative to, say, our genetic code or the genetic code of any real animal or even a plant. And so, why do I bother calling it a genetic code? Why don't I just call it, the parameters or something like that? And the answer is because of, what you do with them, which we'll get to in a little bit. So just sort of continuing our journey sort of through history and through the development of the project. In 1999 is when the distributed screensaver came into existence, and when this started to go from just being a graphics project to being a network project. So it was inspired by Study at Home, and the idea is that you can use a screensaver to put all the idle computers out there on the internet to work, and then form a virtual parallel supercomputer for really low cost. And the actual particular inspiration was, I had written this software, and made a couple of test movies and put it on the web as open source and hadn't done much with it for years. And eventually, so somebody else, made a plugin for After Effects, and then, they worked for a sort of a special effects company. And then they actually, where they had a render farm, and they actually made a really cool movie of these things dancing with music. And they put it on a videotape, this was a while ago, and sent it to me. And I was watching it and said, wow, this looks great, but I don't have, all I have is my dinky little PC. It would take me weeks to even just, to render this, let alone, model it. And then that was actually the moment we said, well, let's just do what SETI at Home did and distribute it on the internet, and it will be done for us. So the Electric Sheep client, the first one was written about a week later, and it's open source, it's GPL, and pretty much the way it works is, when your screensaver comes on, your computer contacts the server and it says, give me work to do, and it downloads a genetic code. The server gives you something to render. You render it, and then when you're done, your computer uploads a frame of JPEG to the server and repeats. Well, that's one thread. Another thread goes to the server and tries to download any new, any sheep, any kind of completed animations, and displays them on your screen, by following that video graph. And it became pretty apparent after using this for a while, and users started to accumulate, that the bottleneck in the design was the MPEG video download, because pretty quickly you've got a robot army of computers all hitting your server trying to download MPEGs. Fortunately, I had a legacy account at Carnegie Mellon, and they have a lot of bandwidth. It took them a couple years before they realized that half of it was going to this. And then they shut it off. They told me that they were nice. But it was good, because then I had to fend for myself, and I found other ways, which I'll tell you about later. But anyway, so that's sort of the rendering, that's where the muscle power comes from. But the intelligence comes from this genetic algorithm. And this is also why we really call them genetic codes instead of parameters. So everybody who's running the screensaver, they're watching the screen. If they feel inspired, they can vote and say, I like what I see, by pushing the up arrow key. And if they don't like what they see, they push the down arrow key. So these votes are transmitted to the server, and the sheep, or the designs that are most popular, have sex with each other and reproduce. And there's mutation and crossover operators. And so you probably know mutation is you just add some noise, or pick a random coefficient and add a random number to it. And a crossover is a little more complicated. That's when you actually take two genetic codes and lay them down side by side and sort of take pieces from each of them in order to build a composite. That's really what sex is. Mutation can be asexual. But the result, though, is that you end up with producing new sheep that actually look like their parents. And there's a lot of, in the art world, this whole genetic algorithm thing actually caught on quite a while ago, like 10 years ago. A lot of people have used it. But frequently, it's effective. It's a completely random process. If there's not, when you modify the parameters, if the resulting image changes completely, then the genetic algorithm is no longer a sort of a hill climbing kind of search algorithm. It's more or less just hit or miss random search. So it's really important when you do these genetic algorithms that the mutations and the crossover operators not sort of step too far. So here's an example showing a happy parent and eight of its descendants. And I think you can see that there's definitely, a resemblance. So then we decided that evolution wasn't good enough and introduced intelligent design into the system. And I resisted calling it that for a long time because, for the obvious reason. But it's actually a perfect description of what's going on. And so I accept it. And so what is going on? More or less, somebody wrote a genetic editor, which is a standard Windows GUI program that where you can edit the genetic code directly, and it has a whole bunch of things that you can sliders and things that you can drag around with a mouse, and lots of little dialogues where you can type in numbers. And while you're doing this, it shows you the image that that this genetic code would produce in draft mode in real time. And so when users come up with something that they like, they can use a menu command to sort of post it into the gene pool and sort of submit it. And it gets distributed to everybody's machine. It shows up on their screens, and if it's popular, if people vote for it, then it will reproduce, and sort of variations of it will appear. And an important part of that is that the intellectual property part, which is, more or less we have artists who are submitting artwork to this, web server, and so, and then I'm making derived works from them, so I need permission to do that. And so the server requires that all the sheep that are submitted to it or posted into it be Creative Commons attribution licensed. And that means that's part of what makes this thing a sort of a collaborative enterprise, is that anybody can improve or learn from anybody else's design or download it and sort of see how it works. So in the fractal design community, which is really different from sort of most of the fractal design community, where people are normally really secretive about their parameter sets and their sort of techniques. And one kind of interesting experiment I did last year was to do a comparison of this genetic algorithm against the sort of human design team. Because and to see, which is better, the robot or the monkey? And the answer was it was almost a tie. I compared the peak ratings of the sums of peak ratings. So I took the sort of the sum total rating of all the sheep that had been submitted by people, and the sum total rating of all the sheep created by the genetic algorithm. And they were, I guess if the people submitted 1, then the GA submitted 1.1. And so I think of that, I call that a creative amplification, because really if you looked at the stuff that the genetic algorithm had done, it was less original than the things that the people had done, but there was sort of more of it. So if you think of yourself as an artist, it's kind of like it's just, or like as a musician, it's like you do some particular drawing or you have some idea, and then the software just sort of like tinkers with it and creates more stuff like that that's kind of different. And so it's kind of like amplifying your work. And so I think you can, part of my objective then when I tinker with the algorithm is to try to boost that number up. And if I can make the GA smarter, then it will increase the amplification factor. And ultimately I want to sort of like have it diverge and go to infinity, and then at that point you can say that, well, then the AI is sort of being creative in its own right, because you don't have to put anything in, or even if you put in one tiny drop of creativity, it will be able to amplify it into something worthwhile or real. So here's a screenshot of the apophysis. Okay, and so just moving on, I think in 2005, about this time of last year, is when I began working on the high fidelity thing. And the Screensaver runs at normal video resolution, 640 by 480, and 9 megabit MPEG, it's stored as 9 megabit MPEG-2. And each sheep is 128 frames long, which is about 4 or 5 seconds. But the thing that I showed at the beginning of the talk is 1280 by 720, so it's 3 times as many pixels. Each sheep is, well, it says 800 here, but it's actually 1600, and there are 15 megabit MPEG-2s, or MPEG-4s. So it's a whole lot more data. I think it takes 20 times the computational energy to render one of these sort of high definition sheep versus one for the Screensaver. And the whole thing would have taken over 1 million hours to render. And there's 1,100 sheep on the hard disk, and it would take 9 hours for you to watch them all if you played them end to end. You know, but they're not played end to end. They're played with this sort of graph following thing, which means you'd have to watch for a very, very long time before you saw the whole thing. You know, you can imagine, you know, wandering through a city at random, how long before you saw every house or something like that. And the Dreams in High Fidelity thing, it premiered in March of this year. I finally called it finished. And I immediately started working on the successor, which is now up to 80 gigs. And that's what I'm showing you now, actually. It's not finished, but it's good enough for an informal thing, and I'm sure you guys want to see my latest stuff, right? But, and I'll show you some more of it at the end when we go into the QA. So some interesting things happened on the way to making this. It wasn't just, oh, well, turn up the resolution. Because it's those little factors of 10 that cause you to like rewrite some code. In particular, one of the interesting thing that I encountered that maybe you guys might be familiar with was bad frames. You know, I was watching it, and every once in a while the screen would like, you know, flash white or black, or more mysteriously half white or half black, or other just weird sort of deformations. And I was pretty baffled. Of course, I thought it was just my mistake. But eventually I realized that it wasn't. It was you know, like bad RAM or cosmic rays or, you know, other just kind of, you know, you're dealing with people's home machines out there on the internet, and you know, they're flaky in strange ways. In particular, in this program, there's this sort of window of danger, which is, you know, after the final image has been encoded as a JPEG, but before the TCP/IP checksum has been computed, if you flip a bit in that data and then decompress it, you'll get a bad frame. So if there's any kind of damage after the TCP checksum has been computed, then, you know, it'll be detected, and, you know, the network code will fix it. And if you flip a bit in the frame buffer while the image is being rendered, you'll end up with just, you know, one bad pixel. And one bad pixel for one frame in an animation, you're probably, you know, you're not even going to see it. But anyway, so I had this really this infrequent problem. Oh, and vandalism too, which you can't fix, at least. So I had decided I had to just address it. You know, whether or not it's my bug, it's just this guy. I have to protect myself from this kind of random behavior. And so I sort of did the obvious thing, which is redundancy. And so each frame gets sent out to 4 different computers. And the results are averaged, and then it checks if the difference between the inputs and the outputs is over some threshold. And if it's over the threshold, it redoes all 4. So it works great, but it sounds like a recipe for, you know, losing a factor of 4 out of performance. It turns out it actually, the redundancy is not wasted because the rendering algorithm is stochastic, so there's naturally noise in the image. And in fact, the noise is inversely proportional to how long you render it. So averaging the 4 images and then averaging them together actually gives you the exact same result you would have gotten if you would just run it for 4 times longer. So actually doing this sort of splitting up and averaging thing doesn't actually waste any time at all. I mean, there is overhead per frame, and in particular, there's the inbound bandwidth to the server, which is more expensive because of this. But the end result, as far as like keeping the high quality, you know, the perfect quality of the image up, is successful. So just a few numbers to sort of characterize the user base or the community of this thing. There's about 35,000 users every day, and it just keeps going up. Actually, yesterday was higher. About 1,000 people vote per day. It renders about 35 sheep and about 105 edges between sheep. Those are standard resolution, not high definition. About 10 sheep are posted, and maybe there's like about 5 posts on the forum or in the email list and stuff like that. So there's a certain amount of kind of like talk and chatter, and people sort of know each other and stuff like that. And there's various kinds of personal drama. Mostly designers who feel that their brilliance is not recognized. Who then of course, you know, people who vote for their own work and post from multiple computers pretending to be different people, and you know, all that kind of stuff. So it's the internet, right? And so I've had to develop a lot of kind of like, you know, defenses in the system. But anyway, so the idea here is I've got this, you know, high definition thing, but I can't distribute it on the internet because it's way more bandwidth than this low resolution stuff which we're already doing. And bandwidth is the bottleneck. So I decided to sell it. And this would be great because you know, it's been an open source project for years, and so I need to find a way to, you know, a way to make money so that I can keep the free network going. And so the idea was to sort of to turn this bandwidth, the lemon of my lack of bandwidth, into the lemonade of of an income. So there's one of these self-contained computers right there, and it's an interesting question, like, you know, how legal is this? For example, if I had used the Creative Commons attribution share-alike clause, then I probably couldn't do this because the resulting video would be required to be share-alike, and so then I wouldn't be able to sell it to somebody and say, you can't give it to all your friends. So it was actually, so I've sort of, in some sense, I've sort of switched from, and actually, when I originally did it, the original Electric Sheep years ago, it was attribution share-alike. And I changed it, so I sort of went from the GPL to BSD licensing for my video in order to make this work. Yeah, so the idea is that there's sort of it would be a symbiotic relationship between the free version and the high definition version, where the free version provides like the design laboratory and computational muscle, and then the high definition version provides the business side. So partly this was like, you know, I think of this as artificial life, you know, where I've got these like, you know, virtual sheep that like live and die and stuff like that. So it's kind of like taking the idea of artificial life to the extreme, where you sort of try to really make, you know, what is the most, you know, thing, you know, lifelike thing that's not really alive, and the answer is, you know, like corporations. You know, that's where the virtual is really becoming real. So that's the direction I'm going. Just a little bit about bandwidth here. After Carnegie Mellon kicked me out, I got onto the Coral Content Distribution Network, which is it's kind of like Akamai, and it's a NSF-funded research at NYU. But they, after I signed up, they had to institute bandwidth caps, 250 gig a day, which was a far cry from the 20 terabytes per day that would be required to actually deliver all the sheep to all the users. And so the problem right now, and the reason there's only 35,000 users, is that each user is only getting a tiny fraction of all the sheep. And so when somebody installs the software on a fresh computer, they contact the server and maybe they get nothing because the cap has been exceeded. So they get a blank screen. Or you only get a little bit per day. So the thing has kind of grown to the, it's like the Peter principle or whatever. It's grown to the point of its collapse. And it needs more bandwidth in order to grow faster. So the obvious solution is BitTorrent, which is what we're wrestling with putting in right now. And it's great because the idea then is that you can, just like with SETI at Home, the distributed supercomputer shares computation across the network. With BitTorrent, we can sort of share the bandwidth load across the network. And so the server has an RSS feed of torrents, and it's now delivering between 1.5 and 2.5 terabytes of video per day to the audience. And I was just informed it's not 10,000 users, it's 12,000. But only, 1,600? By the way, Dean Godet is one of the people who's contributes to the project, and he runs the machine that hosts it, and is, especially the last year or two, has done a lot of optimization of the server. So the reason some of these numbers are as they are is mostly because of his work. And anyway, so only about 20% of the BitTorrent users actually have their firewall forwarding the ports correctly so that they can actually upload. And it's not enough for the swarm to support itself. So we gotta do the UPnP thing, and we don't really know how we're gonna fix it, but we're working on it. So just a little future history. Where I'd like this to go is to make it a sort of self-supporting creating system that's fully decentralized and using distributed hash table. And I want it to be like a computation that you can tune into from anywhere, that doesn't have any physical location but just exists strictly in cyberspace. And I would like to, keep extending the genetic code. Every year I add sort of more operators to it, more functions to it. But I would like to really turn it into a real language, effectively a Turing-complete programming language, so that the network can support really open-ended evolution. And then ultimately, birth of a network resident life form. So some kind of AI thing. So that's where I'm going. And it's been the work of a lot of people, and not just Dean and me. Here are their names, and especially also I want to mention Paul Graham for his financial support, and let's see. And that's pretty much it. Those are the URLs, and we definitely need more programmers, especially for the clients like Windows and Mac, people who can do graphics and networking. So if anybody here can program, then give me a ring. And I think we have time for questions. So have at me. Oh, and let's turn the video back on. So.
how much voting there is and how much it can tweak the system? Like, how do you actually distribute that to allocate computing resources for the GAs and stuff?
Right. So the question is, how does the voting actually affect what the genetic algorithm does? And the answer is, every time the system wants to create a sheep, it looks at the current flock and picks the parents. And basically, the original system was every vote that you got was like a lottery ticket for reproduction. And so your chances of reproducing was proportional to the number of votes you got. I found that resulted in kind of a winner-take-all system because the distribution of votes also follows a power law. There's a few sheep that are really popular, and then there's a whole lot which are not so popular. And more or less, the guys who had hundreds of votes were doing all the reproduction. And so I changed it to, again, be a logarithmic system. So it's kind of like I instituted progressive taxation or something like that. And you know, I don't want to say I'm like a benevolent or anything like that. I mean, nobody like kills more sheep than I do, but I've found that it kind of had better results. And I think it's kind of interesting to think about, like, you know, using these kinds of systems as test beds to find out, like, you know, where we can actually tinker with the system and find out what works. Any other questions?
Since you're usually watching a video between two sheep, right? Like between two and
It's half the time.
So when you vote, does it count for one of them or both of them? Or?
If you vote during a transition, it's ignored. There's plenty of votes that are right on, and I could probably glean more information by splitting it like you recommend, but I just never got around to it, and it seems okay.
Have you considered having when a sheep reproduces, it kind of goes out of the gene pool for a little while, maybe gets tired?
That never occurred to me.
Eat a lead sheep, not eating the other Western
I've noticed on the Screensaver you sort of have generations where you like wipe the slate clean and start from a totally new set of sheep.
Yes, well, you've been running it for a while because that hasn't happened in a while. But
yeah, why do you do that?
why do I do that? There's two answers. One is the reason that it deletes stuff is because if I start a new generation, it could be with incompatible parameters, and so, you know, where you couldn't do a transition. And so, for example, if I change the resolution, I wouldn't be able to the MPEGs are just immiscible. But in fact, sometimes, you know, if there's just because of a server crash or I screw up while I'm programming the server, I have to reset the database, and then it can just be an accident, or it can be because I want to like make an incompatible change. But so if you want to not have all your sheep deleted, you can back them up yourself, just like any data file. But then after the generation change comes around, you can put them back into your cache folder, and they will play. Unless they're like unless they really are incompatible, in which case you're out of luck.
How will these breaks compress?
Well, as into video or as a JPEG? I use quality 90 JPEGs. And then this is 15 megabit MPEG 4. So I mean, it compresses into, the video compressor hits the target, so I'm not, but as far as like the size of the JPEGs, I don't know, it's like a 200K? I don't know.
It just doesn't seem like it's very well suited to the nature of JPEG. Yeah.
The content, you mean?
Yeah.
Yeah, well.
Is there a better algorithm?
Yeah, there's.
The server has to decompress every one of them. So
It defeats the point, yeah.
And so you don't like need a big server.
I don't know. I mean, I definitely have some issues with the video compression. I mean, I think it's really just because I use mencoder, and it freaks out sometimes. You'll see it if you watch. Everything goes blocky or worse. But, you know, so that's open, it's open to change. But I think JPEG works pretty well. In back?
Robots versus monkeys. Have you done some sort of correlation study on whether the genetic algorithm actually increases votes or preserves votes?
I couldn't quite understand the last bit. Whether the genetic algorithm preserves votes?
Whether there's a correlation between performance and evolution. Make sure that it's better than random.
Oh, well, I'm sure it does a lot better than random. I mean, if you pick, I have compared random genomes where I have, you know, the basis of any genetic algorithm is you have to start out, you know, you have to start with something. So I can create random stuff. And if you compare those to the things that were produced by the GA, the GA produces stuff that's much better. But it's certainly true that if you give a sheep of some rating, of some quality level, and give it to the GA and say, you know, make some children, make some mutations, almost all of the children mutations will be of lower quality. It's just a fact of life, you know, most mutations are bad. And so in general, if you look at sort of successive generations, instead of seeing what you would think of with evolution, whereas, you know, every generation is smarter and better than the previous, you know, like us, but you can, you know, in fact, there's actually degeneracy. Every generation is uglier and stupider. But, you know, that's the way I'm trying to address that is more or less by having more children. And so, because it's, yeah, it worked last time, right? You know, because it's a random process. You know, with the GA, basically you got to get lucky, and you got to keep trying if you want to get lucky. And so, and in particular, what I've done is I got the sheep weren't being produced fast enough. There's, you know, 35 per day. You know, it's just not a large enough population to really get some winners. And so, as of a couple months ago, I instituted something I call the brood, which is every day the server generates, instead of rendering some sheep, it renders hundreds of potential sheep. So instead of an animation, it renders a sheep where every single frame has a different genome generated by the GA. And this doesn't get compressed with MPEG, but it pops up, you know, basically on my web control panel, and I screen out the ones that I like and send those sort of through. And so more or less what this does is it makes the genetic algorithm search much broader, about a factor of 5 wider search, and the results are much better. So it's been running a whole lot better lately, and I'm looking for other ways to sort of continue to improve it like that. I want to say one more thing about that, which I didn't say in the talk, is a lot of effort that I've put in lately is actually sort of developing this kind of web control panel for the flock. And so when I started doing the high definition stuff, that's when the light bulb went on in my head, and I realized, oh, like, I have a sort of a supercomputer at my disposal. You know, and it turns out it's as if I had somewhere between 5,000 and 10,000 node cluster dedicated. You know, I need an interface to control it, or I need an interface to design sheep, you know, that harnesses this supercomputer. And so there's a lot of stuff in the server now which you can't see as users, which are actually stuff that I use for like finding edges and sort of like searching through lots of potential sheep and different ways of connecting them together, and then picking out the good ones to eventually appear in either high definition or in the screensaver. So there's a lot of this funny design stuff. Okay, so where was the question that was over here? In the red shirt?
So does any of the MPEG compression happen in a distributed way, or is that just on the server?
All the compression is on the server. And is there a reason for that? Oh, well, it's the easiest thing to do. And it's not a bottleneck.
Very low. It spends like 600 seconds a day on MPEG compression. It spends like 8,000 seconds a day on decoding JPEGs.
Yeah, so it's more or less, M encoder is really fast, And ultimately, everything should be distributed. And then that will be really cool. But, you know, not yet. Oh wait, somebody new, you.
Have you investigated using like collaborative filtering or something to encourage more votes? Because if you vote, you get more sheep that are like the kind of sheep you like.
I've thought about it. I think it's a great idea to sort of combine, you know, in some sense, evolution is really stupid, right? But in collaborative filtering is like way smarter because, you know, with you get sort of what you want instead of, you know, filtering everybody through the pinch point and getting the lowest common denominator. So some kind of hybrid between evolution and collaborative filtering I think would be great. Just haven't got there yet. I think it's actually pretty hard because, well, to start combining it with BitTorrent, because with the torrents, the sheep actually get packaged together into like packs of like, you know, 20 or more. And so then you can't just download the exact ones you want. You have to get them in groups. You know, but maybe someday we'll figure it out. You?
Do you want the sheet ratio fixed, or the edges, like how many edges did from any one sheet or two sheet get turned into IBOT?
The way it works is every time it creates a sheep, it creates one edge to it and one edge away from it, which is essential, otherwise you can't play it. And then it also creates another random edge between two other random sheep. And so what that happens though is that means that you start out with, you know, one input and one output, but then if you live for a while, and, you know, sheep that aren't so popular die pretty quickly, but the sheep that stick around eventually get hit by that sort of random edge. And so the ones that are higher quality and longer lived accumulate more edges. And so there's more ways of getting to them, and so they show up on your screen more often. All the way in the back?
How do you make the colors now stable, and also do you ever recolor any of these things?
I think the question was, where do the colors come from, and do I ever recolor them? Is that right? Okay. So the colors originally came from this sort of algorithm where I could give it an image, and it would derive a palette. But then eventually we opened it up to sort of in that design program where people could put in any palette they wanted. So when people, and that software has that algorithm built into it. And so the easiest way to get a palette is just from a photograph whose colors that you like. But people also hand design their own palettes. But then once they're in there, then they start evolving. And so they're just part of the genome. And each of the transformations kind of has like a color coordinate associated with it that says where in the palette it converges on. And so more or less there's like the subset of the palette that actually gets used and displayed is just evolved. I almost never correct or fix or change any parameters or any, you know, colors or not. I pretty much leave the sheep as the, you know, I just work as an editor. I either like them or I don't like them. I try not to try to tweak them. Not 100%, but 99%. So you?
Using the inverted data to upweight or downweight the edges to change the transition properties.
I don't understand.
So you said you control maybe votes and
Yes.
between different votes.
Yes.
Are you thought of using that to vary the transition property?
Oh. You could do that. The probabilities are we out of time? Okay. We're out of time. But actually the probabilities are all, the edge probabilities are all even. So they're never vary. It just picks randomly. I think those decisions are made locally, not according to like the server. So it would be hard to sort of transmit that information. But I think locally you could, especially based on an individual user's voting, determine what gets played back on their machine more based on their voting, in addition to sort of affecting the genetic algorithm. And, you know, I think that's a good idea, and we haven't done it. So let's see, where's my host? There you are. So if we're out of time, then we quit. All right. So thank you very much.